Every force that has ever threatened life on Earth, every storm, every volcanic eruption, every mass extinction, operates within a narrow band at the very bottom of what the universe is capable of producing. This documentary travels beyond that band, into places and phenomena where the physics that governs ordinary existence either breaks down entirely or reaches values so extreme that new rules take over. The science is real. The measurements are confirmed. What follows is what nature actually looks like when it is not being gentle. On the night side of Earth, on the 27th of December 2004, the sky looked ordinary. No warning. No visible sign of what was already arriving. A pulse of energy had been traveling for 50,000 years, crossing half the diameter of the Milky Way, spreading outward through interstellar space, and it reached our planet in a fifth of a second. The instruments designed to measure the most energetic events in the universe went beyond their maximum readable range. A spacecraft orbiting Mars registered the same event. The signal reflected detectably off the Moon. On Earth, the upper atmosphere was disturbed as though a significant solar flare had struck it. All of this from a single object, on the far side of the galaxy, that released more energy in that fraction of a second than the Sun will produce in 250,000 years. That is one object in one chapter of 14. Each chapter in this documentary examines a place or phenomenon where the physics that governs ordinary existence either breaks down entirely or reaches values so extreme that new rules take over, not dramatic language. Actual measured values, temperature, radiation flux, gravitational tidal force, particle energy, pressure. Across the universe, each of these parameters reaches levels so far beyond everyday experience that stating the numbers without context is almost meaningless. A figure with 15 zeros attached to it does not become comprehensible simply by being large. It becomes comprehensible when you have climbed to it from something familiar, rung by rung, until the scale is felt rather than merely processed. That is what this documentary is for. Start with temperature, because it is the one dimension of danger every human body understands directly. You have felt the difference between a warm room and a cold one. At 41 degrees Celsius, the human body begins to suffer irreversible damage. At 100 degrees, water boils. The surface of the Sun sits at approximately 5,500 degrees, hot enough that no material humans have ever manufactured could survive proximity to it for more than fractions of a second. In the final second, before a massive stellar core collapses into a neutron star, the temperature at its center reaches approximately 10 billion degrees. Each of those steps is not a little hotter than the one before. Each one is a different physical regime, governed by different processes, producing different forms of matter and energy that simply do not exist at the step below. Radiation tells the same kind of story, but the ladder is harder to climb because radiation is invisible. You cannot feel it arriving. A single full-body dose of 450 rads is lethal to half of all humans within 30 days without medical treatment. Standing on the surface of Jupiter's moon Io, an unshielded human body would absorb approximately 3,600 rads in a single day. That is 8 times the lethal threshold, delivered continuously every day as a baseline condition of simply existing there. And Io is nowhere near the most radioactive environment in the solar system, let alone the universe. 3 benchmarks will appear throughout this documentary, and it is worth understanding what they mean before the objects that exceed them arrive. The first is the Eddington luminosity. Picture a star as a constant negotiation between 2 forces: gravity pulling inward, radiation from nuclear fusion pushing outward. The Eddington luminosity is the point at which the outward pressure of a body's own light exceeds the inward pull of its own gravity. For a body of 1 solar mass, that threshold sits at approximately 3.2 times 10 to the power of 31 watts. Cross it, and the object begins to lose mass. Radiation overcoming gravity and driving the outer layers into space. Several objects examined in later chapters radiate beyond this threshold as a routine condition of their existence. The second is the Schwarzschild radius. For any mass in the universe, there is a radius to which that mass would need to be compressed for its escape velocity to equal the speed of light. Nothing moving at or below the speed of light could escape from its surface. For Earth, that radius is approximately 9 millimeters, smaller than a marble. Compress the entire mass of the Earth into a sphere smaller than a marble, and light itself could not leave it. For the Sun, the Schwarzschild radius is approximately 3 kilometers. These numbers define the threshold at which black holes exist. The third is tidal disruption force. Gravity does not pull uniformly. The side of any object closer to a gravitational source is pulled more strongly than the side farther away. On Earth, the Moon creates this difference across the diameter of the oceans, and the result is tides, a twice-daily rise and fall of water that most people experience without giving it a second thought. In the vicinity of a neutron star, the same difference measured across the diameter of a human body would exceed the tensile strength of matter itself. The body would not be crushed. It would be stretched, pulled into a lengthening thread along the direction of the gravitational field, until the molecular bonds holding it together failed entirely. This process has a name: spaghettification. It is not a metaphor. It is a calculated physical outcome with a known threshold and a confirmed mechanism. Against this framework, the most extreme conditions ever recorded at Earth's surface register near the absolute lower boundary of what the universe can produce. The highest air temperature ever reliably recorded on Earth's surface was 56.7 degrees Celsius, measured at Furnace Creek in Death Valley in July 1913. The most intense natural radiation environment a human has ever survived remains orders of magnitude below the baseline conditions on Io. The tidal forces accessible anywhere on or near Earth are gentle enough that the oceans respond to them twice a day, and living things have built their biological rhythms around that rhythm for hundreds of millions of years. Everything that follows is measured against that baseline. The distance between that baseline and what comes next is what this documentary is about. Picture a world almost identical to Earth. Similar size, similar mass, closer to the same star, receiving about 90% more solar radiation than Earth does even before its atmosphere transformed. Formed from the same cloud of gas and rock at the same moment in the same solar system. Give it oceans. Give it a water cycle. Give it the early conditions that, on Earth, eventually produced everything alive. Now watch what happens over the next 4 billion years when one feedback loop goes wrong and nothing corrects it. That world is Venus, and what it became is the most hostile surface in the solar system. On the 1st of March 1982, a Soviet spacecraft called Venera 13 entered the atmosphere of Venus and began its descent. It had been traveling for 4 months. The probe was armored against what it was about to encounter, designed to withstand pressures and temperatures that would destroy ordinary engineering within seconds. It reached the surface, transmitted data, and was destroyed by its environment in 127 minutes. Venera 13 was the latest in a series of Soviet landers reaching back to Venera 7 in 1970, the first spacecraft to transmit data from another planet's surface. Each mission added to what we know about Venus. What Venera 13 added was this: a surface temperature of 457 degrees Celsius, a surface pressure of 89 atmospheres, and the first true color photographs of the Venerian surface. Orange-lit slabs of volcanic rock extending to a haze-obscured horizon, taken less than 42 million kilometers from Earth. Hold those numbers for a moment before moving on. 457 degrees Celsius is hot enough to melt lead, which liquefies at 327 degrees. and zinc, which melts at 419. It is hot enough to anneal certain aluminium alloys, and it is not a peak temperature recorded during the day at the equator. It is the sustained temperature everywhere on Venus, day and night, equator and poles, at all altitudes below the cloud deck. Venus shows almost no day-night temperature difference at the surface because its dense atmosphere spreads heat across the entire planet. The heat is locked in, held by an atmosphere so thick that no variation in solar angle makes any measurable difference to the surface below. The pressure at 89 atmospheres is equivalent to standing 900 meters below the surface of Earth's oceans. At that depth, the pressure would crush an unprotected human body in under a second. On Venus, it is simply the air. Above the surface, between roughly 45 and 70 kilometers altitude, the atmosphere contains dense clouds of sulfuric acid, not a trace contaminant. The dominant cloud-forming material across the entire planet. The acid concentration within those droplets reaches between 75 and 96%. Rain falls from them but evaporates before reaching the surface, returning sulfur compounds to the cloud layer in a sustained chemical cycle. The atmosphere itself is 96.5% carbon dioxide, with most of the remainder being nitrogen. There is no oxygen. There is no water. There is nothing that would register as breathable or drinkable by any standard a living organism on Earth would recognize. None of this is what Venus was always like, or at least, the evidence strongly suggests it was not. Venus and Earth formed from the same region of the early solar nebula approximately 4.5 billion years ago. Their bulk compositions are nearly identical. Venus is 95% of Earth's diameter and 81.5% of its mass. Its uncompressed density differs from Earth's by less than 2%. These are the numbers of sibling worlds, formed under comparable conditions from comparable material. Early Venus very likely had liquid water. Planetary formation models indicate it would have received a similar flux of water-bearing impactors as Earth during the late heavy bombardment period. Spectroscopic analysis of the current Venerian atmosphere reveals a deuterium to hydrogen ratio approximately 150 times higher than Earth's. That ratio is consistent with a world that once held large quantities of water and lost the lighter hydrogen preferentially to space over geological time, leaving the heavier deuterium enriched in what remained. The atmosphere of Venus carries a chemical memory of an ocean it no longer has. The process that transformed Venus from a potentially temperate world into what Venera 13 recorded is called the runaway greenhouse effect. The greenhouse effect in its moderate form is not a threat. It is what makes Earth habitable. Sunlight passes through an atmosphere and warms the surface. The warmed surface radiates energy back outward as infrared radiation. Certain gases, including water vapor, carbon dioxide, and methane, absorb that infrared radiation and trap heat that would otherwise escape to space. On Earth, this mechanism raises the mean surface temperature by approximately 33 degrees Celsius above what it would be on an airless world at the same solar distance. Without it, Earth's average surface temperature would sit at around minus 18 degrees Celsius. The greenhouse effect, operating within limits, is the reason liquid water exists on this planet. The runaway variant removes the limits. As temperatures rise, more water evaporates from the surface and enters the atmosphere. Water vapor is itself a potent greenhouse gas. Its increased concentration drives further warming. Further warming drives further evaporation. The feedback accelerates. At a certain threshold, the system cannot stabilize. The oceans evaporate completely, with no surface water remaining to participate in the carbonate-silicate cycle, which on Earth draws carbon dioxide out of the atmosphere and locks it into rock over geological timescales. Carbon dioxide accumulates without limit. The atmosphere thickens. The surface bakes. The process becomes irreversible on any timescale relevant to planetary habitability. Whether Venus crossed this threshold through gradual warming, a sudden volcanic outgassing event, or some combination of both is not settled. Climate models of early Venus differ significantly in their treatment of cloud feedbacks. Some suggest that Venus, rotating as slowly as it does, once every 243 Earth days, may have had stabilizing cloud cover on its day side that delayed or partially prevented runaway warming for billions of years. Others suggest the transition happened relatively early. The data needed to distinguish between these scenarios has not yet been collected. What the Venera program gave us was confirmation of the endpoint: the temperature, the pressure, the acid clouds, the carbon dioxide atmosphere. These were measured directly from the surface by instruments being destroyed as they transmitted. What Venera 13 also gave us, in its 127 minutes of operation, was a set of images that remain among the most alien photographs ever taken within our own solar system. Orange-lit volcanic rock under a sky the color of amber, lit from above by a sun that never fully penetrates the cloud deck. A horizon lost in chemical haze. A surface that has not changed in any meaningful way for hundreds of millions of years and will not change for hundreds of millions more. That is what makes it instructive. Not a warning about the distant and the alien, but a warning about the near and the familiar. About what happens when a feedback loop that could in principle affect any planet with an atmosphere and water is allowed to run without correction. The danger Venus represents requires no exotic physics, no neutron stars, no relativistic jets, no quantum instabilities. It is the product of carbon, oxygen, hydrogen, and sulfur interacting through chemistry and atmospheric physics under conditions that began as familiar and became irreversible. The question of whether Venus represents a fate Earth could share is one that planetary scientists treat with care rather than alarm. Earth sits at a greater distance from the Sun, receives about 28% less solar radiation at the top of its atmosphere than Venus does, even accounting for its higher reflectivity, and maintains the carbonate-silicate cycle as an active long-term carbon sink. Current evidence does not suggest Earth is approaching a runaway threshold, but Venus demonstrates, with the specificity of a controlled experiment run at planetary scale, that the transition from habitable to uninhabitable is not merely theoretical. It happened. It is documented in the ratio of isotopes left behind in an atmosphere that used to contain an ocean. 2 upcoming missions are designed to move the science forward. NASA's Da Vinci probe, planned for the early 2030s, will descend through the Venerian atmosphere, sampling its composition at multiple altitudes, with particular focus on the deep atmosphere below the cloud deck where the chemical record of Venus's early history may be partially preserved. The European Space Agency's Envision mission will map the surface and subsurface using radar and spectrometry to determine whether Venus remains volcanically active today. Together, they are expected to substantially narrow the range of models describing what Venus was before it became what the Venera program found. Until that data arrives, Venus occupies a specific and sobering position in planetary science. It is the most hostile surface in the solar system, not because it formed differently from Earth, but because it did not. Its danger is a product of shared origins and divergent history. A feedback mechanism that, once initiated, had no corrective response available to it. The temperature held, the water left, the carbon stayed. That is what 127 minutes on the surface cost Venera 13 to confirm. Find Jupiter in the night sky and you are looking at the largest planet in the solar system. A world so massive that more than 1,300 Earths could fit inside it. Now imagine orbiting that planet at a distance of 422,000 kilometers, roughly the same distance as our moon orbits Earth, but around something 318 times more massive. Imagine what that gravity would feel like if you could feel it, not as a gentle pull but as a constant rhythmic squeezing, a force that rises and falls with every orbit, deforming the ground beneath your feet by up to 100 meters with each pass. You would be standing on the most volcanically active body in the solar system, and the heat under your feet would have nothing to do with the sun. That is Io. And what is happening to it is one of the most direct demonstrations in the solar system of what gravity does when it cannot simply hold something still. On the 2nd of March 1979, 3 planetary scientists published a paper in the journal Geophysical Research Letters. Stanton Peele, Patrick Casson, and Ray Reynolds had been working through the orbital mechanics of Jupiter's innermost large moon, and the mathematics led them to a conclusion they stated directly in the paper's final line. They predicted that Io may currently be the most intensely heated terrestrial body in the solar system, and they suggested that active volcanism was a probable consequence. 3 days later, Voyager 1 flew past Io and confirmed it. Navigation engineer Linda Morabito, processing Voyager's images to identify background stars for positional calibration, noticed an anomalous plume extending from Io's limb into space. It was 280 kilometers high. It was a volcanic eruption caught mid-event by a spacecraft that had not been sent to look for one. Over the following days, Voyager's cameras identified 8 active volcanic plumes on a single moon. Peele, Casson, and Reynolds had been right. The mechanism they had described 3 days before the flyby was exactly what was heating Io's interior. That mechanism is tidal friction. Io is the innermost of the 4 large moons that orbit Jupiter, the group collectively known as the Galilean moons, after their telescopic discovery by Galileo Galilei in 1610. It is roughly the same size as Earth's moon, with a diameter of 3,642 kilometers. It orbits Jupiter, completing one full circuit every 1.77 Earth days. At that distance, Jupiter's gravitational field is immense. But Io does not orbit alone, and that is the source of everything that makes it extraordinary. Europa, the next moon out, orbits Jupiter in exactly twice the time Io takes. Ganymede, the moon beyond Europa, completes one orbit for every 4 of Io's. This 1-2-4 relationship is not coincidence. It is a gravitational resonance, a stable configuration locked in place by the moon's mutual gravitational interactions over billions of years. The resonance means that Io, Europa, and Ganymede periodically align in specific geometric patterns, and during those alignments their gravitational pulls on each other reinforce rather than cancel. For Io, the consequence is continuous. Jupiter pulls it powerfully toward the planet. Europa and Ganymede pull it from behind and ahead in its orbit, tugging it into a slightly elliptical path rather than a perfect circle. An elliptical orbit means Io's distance from Jupiter varies over each orbit. As it moves closer, Jupiter's tidal pull stretches Io along the planet-facing axis. As it moves farther, that pull relaxes, the moon flexes. Not metaphorically, but physically. The solid surface of Io rises and falls by up to 100 meters over each orbital cycle, driven by the changing strength of Jupiter's gravity. To get a sense of what that means, imagine the ground you are standing on rising and falling by the height of a 30-story building, twice every 1.77 Earth days, not from any geological event, but simply from the gravitational rhythm of the system Io is trapped in. Now imagine that happening continuously for billions of years. The flexing generates friction within the rock. Friction generates heat. Heat sustained at this intensity over billions of years has no outlet except through volcanism. The result is a heat flux at Io's surface of approximately 2.5 watts per square meter, globally averaged. Earth's internal heat flux, driven by residual formation heat and the decay of radioactive isotopes, averages around 0.09 watts per square meter. Io produces roughly 28 times more heat per unit of surface area than Earth does, from a completely different source, with no contribution from radioactive decay and no input from solar radiation. The energy comes entirely from orbital mechanics, from the gravitational relationship between three moons and the planet they orbit. At the surface, this heat escapes through more than 400 known volcanic centers. Some produce lava flows of silicate rock reaching temperatures above 1,600 degrees Celsius, hotter than any volcanic eruption recorded in the modern geological record. Stand near one of those flows and the rock itself would glow a dull red at the edges where the lava meets the cooler surface, visible from a distance before any other feature of the flow became clear. Others drive sustained plumes of sulfur dioxide gas and sulfur vapor high into the near vacuum above the surface, some reaching 500 kilometers in altitude, higher than the International Space Station orbits above Earth. Those plumes fall back across enormous areas, coating the surface in sulfur compounds that give Io its distinctive yellow, orange, red, and white coloration. The colors are not random. They are sulfur in different molecular and crystalline forms at different temperatures, a color-coded record of how hot each region of the surface runs. The surface itself is geologically young almost everywhere on it. Impact craters, which accumulate on stable planetary surfaces over billions of years and serve as a standard tool for estimating surface age, are nearly absent on Io. The resurfacing rate is high enough that craters are buried or erased almost as quickly as they form. Estimates based on the volume of volcanic output suggest Io resurfaces itself globally at a rate of roughly 1 to 10 centimeters per year on average, with localized regions experiencing far more rapid deposition. The surface Voyager, one photographed in 1979, no longer exists. It has been buried, recoated, and reworked by 45 years of continuous volcanic output since that flyby. Subsequent missions have deepened the picture. The Galileo spacecraft, which orbited Jupiter between 1995 and 2003, made multiple close flybys of Io and confirmed lava temperatures consistent with rock types associated with very high temperature melting of mantle material, the kind of eruptions that have not occurred on Earth since the Archean era billions of years ago. The New Horizons spacecraft caught Io in eruption during its 2007 Jupiter flyby, imaging the Tavashtar volcano producing a plume 330 kilometers high. NASA's Juno spacecraft has conducted close Io flybys beginning in 2023 and returned the most detailed imaging of the volcanic surface since Galileo. Tidal heating as a mechanism scales with the mass of the central body, the orbital eccentricity it forces on the satellite, and the internal properties of the satellite's material. At the relatively modest gravitational energies of the Jupiter system, it produces Io, a world resurfaced continuously by heat, generated entirely by the pull of its neighbors. At the far greater gravitational energies found around neutron stars and black holes, the same mechanism operates at scales that no solid body could survive. The force that raises and lowers Io's surface by 100 meters becomes, around those objects, something that does not flex matter but dismantles it entirely. What gravity does gently here, it does without restraint elsewhere. Stand near a fire and you feel the heat on your face. Step back and it fades. Step closer and it intensifies. This is not a principle that requires explanation. It is among the most immediate physical experiences available to a human body. Distance from a heat source means less heat. Closeness means more. The relationship is so fundamental that it feels less like a law of physics and more like a definition of what heat is. The sun violates it. The sun's visible surface, the photosphere, sits at approximately 5,500 degrees Celsius. Moving upward through the thin atmospheric layer above it, called the chromosphere, temperatures climb modestly to around 20,000 degrees. Then something happens that should not be possible. Crossing a narrow transition region only a few hundred kilometers thick, the temperature does not continue rising gradually, it leaps. Within a short distance, it reaches somewhere between 1 and 3 million degrees Celsius. The outer atmosphere of the sun, the corona, is roughly 200 times hotter than the surface directly beneath it. Despite being farther from the nuclear furnace at the sun's core and receiving a far smaller fraction of its energy, move away from the fire, feel more heat. The sun does this every day, and after more than 80 years of investigation, no one has confirmed exactly why. This is the coronal heating problem. It has been known since the 1940s, when spectroscopic observations of the corona during solar eclipses revealed emission lines from highly ionized iron atoms, specifically iron, with 13 of its 26 electrons stripped away. Stripping that many electrons from an iron atom requires temperatures in excess of 1 million degrees. The observation was initially met with skepticism because the temperature it implied seemed physically absurd. Subsequent measurements confirmed it repeatedly. The corona is genuinely that hot. The question of why has remained open ever since. To understand why this is so difficult to explain, follow the energy from its source. At the sun's core, a sphere roughly 140,000 kilometers in radius, hydrogen nuclei fuse under pressures of around 250 billion atmospheres and temperatures of approximately 15 million degrees Celsius. The energy produced there does not travel quickly. It moves outward through layers of plasma so dense that a single photon may be absorbed and re-emitted millions of times before advancing any meaningful distance. The journey from the core to the visible surface takes on the order of 100,000 years. A photon produced in the sun's core today will not reach your eyes for 100 millennia. When that energy finally reaches the photosphere, it escapes freely into space, and the temperature begins at 5,500 degrees. By every standard model of heat transport, temperature should then decrease continuously as you move outward. It does exactly that for most of the journey, from 15 million degrees at the center down to 5,500 at the surface. Then it reverses, not gradually, sharply. The corona sits above the surface at a temperature 200 times higher than the surface itself. Thermodynamics forbids heat from flowing spontaneously from a cooler body to a hotter one. The photosphere cannot be heating the corona directly. The energy must be arriving by a different route, through a mechanism that bypasses the ordinary rules of heat conduction and deposits energy into the corona from somewhere other than below. Two candidate mechanisms have dominated the debate for decades, and neither has been ruled out. The first is Alfvén wave dissipation. The sun's surface is not still. Convective motion in the photosphere, hot plasma rising and cooling and sinking in cells, some of them the size of continents, continuously jostles the footpoints of magnetic field lines threading upward into the corona. This jostling generates a type of wave called an Alfvén wave, which travels along the magnetic field lines into the corona above. If those waves deposit their energy in the corona rather than passing through it, they would heat the coronal plasma directly. The difficulty is that Alfvén waves can, under some conditions, pass through a medium without losing much energy at all. Determining whether the wave flux reaching coronal heights is sufficient to account for the observed temperatures requires measurements that have proven technically demanding to obtain. The second mechanism was proposed by the physicist Eugene Parker in 1988. Parker suggested that the corona is not heated by large coherent waves at all, but by an enormous number of individually tiny energy releases, each one far too small to detect directly. He called them nanoflares. The idea is that the magnetic field, threading through the corona, is continuously tangled and braided by the convective motion below. Periodically, tangled field lines reconnect in small localized events, releasing stored magnetic energy as heat. A single nanoflare releases roughly 10 to the power of 17 joules, below the detection threshold of any current instrument. But Parker argued that if such events occur at a rate of perhaps 10 to the power of 26 per second across the entire Sun, the cumulative effect would be sufficient to sustain coronal temperatures. The prediction is internally consistent. It has not yet been directly verified. The Parker Solar Probe, named in honor of Eugene Parker, who died in 2022, is currently the closest any human-made object has come to the Sun. In December 2024, it completed its closest approach to date, passing within 6.1 million kilometers of the solar surface, well inside the outer corona itself. Its instruments have detected structures called switchbacks, rapid reversals in the direction of the solar magnetic field embedded in the outflowing solar wind. Whether those switchbacks are signatures of nanoflare heating, alphen wave dissipation, or some other process is still being worked out from the data. The answer exists in measurements being taken now and has not yet been extracted. What the corona unambiguously produces, regardless of what heats it, is a continuous outflow of plasma and magnetic field into space. Under normal conditions, this outflow is called the solar wind, a stream of charged particles that fills the inner solar system and shapes the environment of every planet within it. At its most violent, the outflow takes a different form. A coronal mass ejection is an eruption in which billions of tons of coronal plasma are launched outward at speeds between 250 and 3,000 kilometers per second. The fastest of these cross the distance from the Sun to Earth in under a day. When a coronal mass ejection reaches Earth, it does not pass harmlessly by. It compresses the magnetosphere, the magnetic bubble that normally shields the planet from the solar wind. It drives geomagnetic storms that generate electrical currents in the ground itself, currents that flow through any large conducting structure, including power grids. In March 1989, a coronal mass ejection struck Earth, and the resulting geomagnetic storm induced currents powerful enough to collapse the Hydro-Quebec power grid in under 90 seconds. 6 million people lost electricity. The blackout lasted 9 hours. Transformers were damaged across North America. The aurora was visible as far south as Cuba and Mexico. That storm was not exceptional by the standards of solar history. The Carrington event of 1859, the largest geomagnetic storm in recorded history, induced currents so powerful that telegraph operators reported receiving electrical shocks from their equipment, and some telegraph systems continued operating even after being disconnected from their power supplies, driven by the geomagnetically induced current alone. A Carrington-scale event striking the modern electrical grid, a grid far more extensive and far more dependent on the kinds of long-distance transmission lines most vulnerable to induced currents, would produce effects that have been estimated in the hundreds of billions to trillions of dollars in infrastructure damage. The corona is not a distant scientific curiosity. It is the origin of a physical process that has already knocked out continental power grids, and that, at sufficient intensity, could do so again at a scale that would take years to repair. The fire that burns the wrong way reaches further than it has any right to. Radiation is invisible. You cannot feel it arriving. You cannot see it accumulate. The damage it does happens at a scale far below anything the body can register in the moment, at the level of individual cells, individual strands of DNA, individual atoms knocked out of their positions in living tissue. By the time the effects become noticeable, the exposure has already happened. This is what makes radiation environments different from every other kind of danger examined in this documentary. The threat does not announce itself. The Galileo spacecraft was built to last. Designed and tested to withstand the radiation environment around Jupiter, it carried shielding rated for a specific cumulative dose over its planned mission lifetime. By the time Galileo was deliberately deorbited into Jupiter's atmosphere in 2003, ending its mission, it had accumulated radiation damage equivalent to 3 times its design tolerance. The spacecraft functioned, but only just. Its onboard tape recorder failed repeatedly. Memory errors accumulated. Systems that should have remained nominal degraded progressively over years of exposure. Galileo did not fail because of a mechanical fault or a software error. It was worn down, particle by particle, by Jupiter's radiation belts. A machine built by some of the most careful engineers on Earth, specifically hardened against the environment it was entering, lasted 3 times longer than its rated tolerance and still ended its mission compromised. To understand why Jupiter's radiation environment is so destructive, start with what a magnetosphere is and what Jupiter's does differently from Earth's. A magnetosphere is the region of space within which a planet's magnetic field dominates over the solar wind, the continuous outflow of charged particles from the Sun. Earth has one, generated by the convective motion of liquid iron in its outer core. That magnetosphere is what deflects the solar wind around the planet, compressing on the sunward side and stretching into a long tail on the night side. Without it, the solar wind would gradually strip away the atmosphere the way it stripped away Mars's atmosphere after Mars lost its own magnetic field billions of years ago. Earth's magnetosphere is essential. It is also, by the standards of what exists elsewhere in the solar system, modest. Jupiter's magnetic field at its cloud tops is approximately 20,000 times stronger than Earth's surface field. The magnetosphere it produces extends roughly 7 million kilometers toward the Sun and stretches into a magnetotail behind the planet, reaching as far as Saturn's orbit. If Jupiter's magnetosphere were visible to the naked eye from Earth, it would appear larger in the sky than the full moon. It is the largest coherent structure in the solar system, larger than the Sun itself when measured by volume. Within that magnetosphere, charged particles become trapped along magnetic field lines, spiraling back and forth without escaping, accumulating over time into radiation belts, orders of magnitude more intense than Earth's Van Allen belts. The particles are not merely trapped, they are accelerated. As they drift through the magnetosphere, interactions with plasma waves transfer energy to them continuously. Jupiter's magnetosphere functions as a natural particle accelerator of planetary scale. Trapped particles in its inner radiation belts reach energies of tens of mega-electron-volts for electrons and hundreds of mega-electron-volts for protons. The practical consequence of those numbers is this. At Io's orbital distance, roughly 422,000 kilometers from Jupiter's center, and well within the most intense belt region, the radiation dose rate for an unshielded human body would reach a lethal level in under 10 minutes. The surface dose rate on Io from Jupiter's radiation belts alone is approximately 3,600 rads per day. The lethal threshold for a human being, a dose that kills half of all people who receive it within 30 days without medical treatment, is 450 rads delivered as a single exposure. Io receives 8 times that threshold every single day as a baseline condition of existing where it exists. The energies this produces are measurable across interplanetary distances. The radio emission from Jupiter's radiation belts, produced by electrons spiraling along magnetic field lines, was first detected from Earth in 1955 by Bernard Burke and Kenneth Franklin using a radio telescope at the Carnegie Institution in Washington. They initially thought they had found terrestrial interference. The signal was real and it came from Jupiter. It was a radiation environment so intense it announces itself across hundreds of millions of kilometers of space. Now take that mechanism, a rotating magnetic field accelerating charged particles, and scale it upward, not to a larger planet, but to an object of a fundamentally different kind. Millisecond pulsars are neutron stars that have been spun up to extraordinary rotation rates by accreting mass from a companion star. Some rotate hundreds of times per second. The fastest known, PSR J1748-2446 AD, completes 716 full rotations every second. Picture an object containing more mass than the Sun, compressed into a sphere roughly 20 kilometers across, rotating 716 times per second. The surface at its equator moves at a significant fraction of the speed of light. Its magnetic field, already vastly stronger than any planetary field, rotates with it. That rotating magnetic field generates electric potential differences that can reach trillions of volts. Particles caught in this environment are not gradually accelerated the way particles are in Jupiter's magnetosphere. They are driven to relativistic velocities, approaching the speed of light within the immediate vicinity of the pulsar. The radiation environment they produce extends outward in the form of a pulsar wind nebula, a bubble of relativistic particles inflated by the pulsar's continuous output, detectable across interstellar distances in X-ray and gamma-ray wavelengths. The step from Jupiter to a millisecond pulsar is a step from a radiation environment that destroys hardened spacecraft over years to one that would be lethal to any unshielded matter within a substantial fraction of a light year. Accretion disks represent a third radiation environment produced by a different process entirely, though the end result sits at the same extreme end of the scale. When matter falls toward a compact object, whether a white dwarf, a neutron star, or a black hole, it carries angular momentum and cannot fall straight in. It accumulates into a flattened, rotating disk around the central object. Within the disk, friction and magnetic turbulence cause material to spiral gradually inward, releasing gravitational potential energy as heat. The efficiency of this process around a neutron star can reach 10% of the infalling mass multiplied by the speed of light squared. To appreciate what that means, nuclear fusion, the process that powers every star in the universe, converts roughly 0.7% of rest mass energy. Accretion onto a neutron star is roughly 14 times more efficient than the most powerful sustained energy production process in the natural world. The temperatures this generates in the inner accretion disk range from approximately 1 million to 10 million Kelvin. At those temperatures, the disk radiates primarily in X-ray wavelengths, pouring energy outward across a broad angle from the inner disk. In the most luminous systems, the radiation output approaches or exceeds the Eddington luminosity, the threshold introduced in Chapter 1, at which the outward pressure of a body's own radiation overcomes the inward pull of gravity. Beyond that threshold, the disk itself becomes unstable. The radiation pushing outward begins to disrupt the inflow of material that sustains it. From Jupiter's belts to pulsar winds to accreting neutron stars, the same underlying physics operates across 14 orders of magnitude in energy. A rotating magnetic field and a source of charged particles are all that is required. What varies is the scale of the object at the center. And across that variation, from a planet to a neutron star, the radiation environment transitions from something that wears down hardened spacecraft over years to something that would restructure matter at interstellar distances. Scale, in this context, is everything. Somewhere in the universe right now, a massive star is in the final hours of its life. Its core has spent millions of years working through every fuel available to it: hydrogen to helium, helium to carbon, carbon through successive stages to silicon, and silicon finally to iron. The iron sits at the center of the star like ash at the bottom of a furnace. It cannot burn. It absorbs energy rather than releasing it. And the moment the iron core grows heavy enough, everything that has held the star up for millions of years vanishes in less than a second. What happens in that second is among the most violent events the universe produces, and what it leaves behind is an object so extreme that the matter inside it exists in forms that have no name in ordinary chemistry. It takes less than a second. When the iron core grows past approximately 1.4 times the mass of the Sun, the pressure holding it up collapses catastrophically. The core falls inward at roughly 1/4 of the speed of light. To put that speed in context, 1/4 of the speed of light is approximately 75,000 kilometers per second. The core collapses across a distance comparable to the diameter of Earth in the time it takes sound to travel a few meters. In under a second, a volume of iron-dominated plasma larger than Earth compresses into a sphere approximately 20 kilometers across. 20 kilometers. The distance you might drive to reach the nearest town. What emerges from that compression is a neutron star. The physics of the collapse is severe enough that ordinary matter cannot survive it. In normal atomic structure, electrons occupy shells around a nucleus, and the pressure of those electron clouds resisting compression, called electron degeneracy pressure, is what holds white dwarfs stable against gravity. In the collapsing stellar core, the density rises past the point where electron degeneracy pressure can resist. Electrons are driven into protons through a process called inverse beta decay, producing neutrons and releasing neutrinos in enormous quantities. The core becomes, within that fraction of a second, a sphere composed almost entirely of neutrons, held up not by electron pressure but by neutron degeneracy pressure and the short-range repulsive force of the strong nuclear interaction. The resulting object has a mass between roughly 1.4 and 2.3 times the mass of the Sun. Its diameter is approximately 20 kilometers. Its mean density is around 4 times 10 to the power of 17 kilograms per cubic meter, comparable to the density of an atomic nucleus. Imagine taking the entire mass of the Sun and compressing it until it fits within the boundaries of a city, not the metropolitan area, the city itself. Every atom that made up a star roughly 1 million kilometers across, now packed into a sphere you could drive across in 15 minutes. A teaspoon of neutron star material transported somehow to Earth's surface would weigh approximately 1 billion tons. To put that another way, it would outweigh every living human being on Earth by a factor of roughly 125,000, contained in a volume smaller than a sugar cube. Surface gravity on a neutron star is roughly 100 billion times Earth's. The escape velocity from the surface is approximately 150,000 kilometers per second, around half the speed of light. These are not poetic approximations. They are calculated values derived from measured neutron star masses and radii obtained through X-ray timing observations and gravitational wave detections. Working outward from the center, the structure of a neutron star divides into layers, each governed by different physics, and not all of them are understood. The outermost layer, the crust, extends inward roughly 1 kilometer from the surface. The outer crust consists of neutron-rich atomic nuclei arranged in a crystalline lattice, similar in structure to a solid metal, but at densities millions of times greater than any metal on Earth. As depth increases and density rises, the nuclei become progressively more neutron-rich, eventually reaching configurations where they deform from spherical shapes into cylinders, sheets, and more complex geometries. These structures are collectively called nuclear pasta, a terminology that reflects their shapes. The cylindrical phase is called spaghetti. The sheet phase is called lasagne. The names are almost absurdly mundane for what they describe. Current simulations suggest nuclear pasta is the strongest material in the universe, with a tensile strength estimated at roughly 10 to the power of 30 pascals, approximately 10 billion times stronger than steel. The strongest steel cable ever made would snap under a force that nuclear pasta would barely register. This remains an active area of theoretical nuclear physics, derived from quantum molecular dynamics simulations rather than direct measurement, but the physics is well grounded and the result is not seriously disputed. This is matter compressed so far beyond everyday experience that new geometries of atomic structure emerge, held together by forces that have no analogue in any material accessible to human hands. Below the crust lies the outer core, a region of superfluid neutrons. A superfluid is a quantum mechanical state of matter in which viscosity vanishes entirely. The fluid flows without any internal friction or resistance. On Earth, superfluidity occurs in helium, fore-cooled to within a few degrees of absolute zero, and when it does, the helium will climb the walls of its container, driven by surface tension with no viscosity to resist it. In a neutron star, neutrons pair up through a mechanism analogous to the Cooper pairing of electrons in a superconductor, entering a superfluid state that persists not at near absolute zero but at the extraordinary densities of the neutron star interior. This superfluid rotates uniformly, threaded by quantized vortices that carry the star's angular momentum. The superfluid interior provides the most compelling indirect evidence for neutron star internal structure currently available through a phenomenon called pulsar glitches. Pulsars, neutron stars whose electromagnetic beams sweep past Earth with each rotation, slow down gradually over time as they radiate rotational energy away. This spin down is steady and predictable over long periods. But occasionally, a pulsar will suddenly spin up, increasing its rotation rate abruptly before resuming its gradual slowdown. These events occur on timescales of minutes and have been observed in dozens of pulsars. The leading explanation is that the superfluid interior, rotating slightly faster than the solid crust, periodically transfers angular momentum to the crust in a sudden coupling event, spinning the observable star up. Each glitch carries information about the fraction of the star's moment of inertia contained in the superfluid component, providing an indirect probe of the interior structure that no direct measurement can yet match. The inner core is where current physics reaches its limit. At densities exceeding several times the nuclear saturation density, the question of what matter actually consists of becomes genuinely unresolved. The neutrons may dissolve into a quark-gluon plasma, a state in which quarks move freely through the medium rather than being confined within individual nucleons. This is matter so dense that the particles we consider fundamental, the building blocks of protons and neutrons, can no longer hold their boundaries. The core may alternatively contain strange matter incorporating strange quarks, or exotic particles called hyperons, that soften the equation of state in ways that constrain the maximum mass a neutron star can support. In August 2017, two neutron stars that had been spiraling toward each other for hundreds of millions of years finally merged. The gravitational waves from that merger, designated GW 170817, were detected simultaneously by the LIGO and Virgo observatories. For the first time, the way two neutron stars deformed each other tidally in their final moments before collision gave physicists a measurement that constrains what the matter inside them actually is. Those constraints have narrowed the range of viable models, but have not selected a unique one. The core of a neutron star remains the densest accessible form of matter in the observable universe. a question sitting precisely at the boundary of what nuclear physics can calculate and what gravitational wave astronomy can measure. Two disciplines approaching the same unknown from opposite directions, neither yet able to see what is at the center. In the summer of 1967, a graduate student at the University of Cambridge named Jocelyn Bell was sitting at a table working through paper. Not data on a screen, not a computer readout. Paper charts, roughly 30 meters of them produced every day by a radio telescope she had helped build, unrolling across her desk in a continuous strip that she analyzed by hand, marking anomalies with a pen, looking for the faint signatures of distant quasars in an ocean of radio noise. In August of that year, she found something that was not a quasar. A repeating radio signal, precise and regular, pulsing every 1.337 seconds without variation. Not approximately 1.337 seconds, exactly 1.337 seconds, pulse after pulse, with a regularity that no natural source was known to produce. The research team labeled it LGM-1. LGM stood for Little Green Men. The designation was partly tongue-in-cheek, but the uncertainty behind it was genuine. Nothing in the natural universe was known to produce pulses of radio emission with that degree of clockwork regularity. The period was too short to be an orbiting binary star system. A pulsating star of normal size would tear itself apart at that frequency. The signal was real, it was repeating, and no one had an explanation for it. By January 1968, Bell had identified 3 additional sources with similarly precise periods. 4 signals of identical character coming from 4 different points in the sky were not the signature of a transmitting civilization. They were the signature of a physical mechanism. The explanation, proposed independently by Franco Pacini and Thomas Gold in 1968, was a rapidly rotating neutron star with a strong magnetic field misaligned with its rotational axis. As the star rotates, the magnetic field rotates with it. Charged particles accelerated along the magnetic poles produce beams of electromagnetic radiation that sweep through space with each rotation, like the beam of a lighthouse seen from a ship. If Earth happens to lie in the path of one of those sweeping beams, a radio telescope detects a pulse for every rotation of the star. The source Bell had found, now designated PSRB 1919+21, rotates 0.748 times per second. Its pulse period of 1.337 seconds reflects exactly 1 full rotation. The name pulsar is a contraction of pulsating star, a slight misnomer since the star itself does not pulsate, it rotates. The pulsing is a geometric effect, a consequence of the beam's orientation relative to the observer. Neutron stars whose beams never sweep across Earth are not detected as pulsars at all, which means the pulsar population we observe represents only the fraction of all neutron stars whose geometry happens to align with our line of sight. The rest spin silently through space, their beams sweeping through directions we will never look along. Ordinary pulsars slow down over time. As the rotating magnetic field radiates energy outward, angular momentum is carried away and the rotation rate decreases. The slowdown is measurable with extraordinary precision. Pulsar timing observations can detect changes in rotation period at the level of 1 part in 10 to the power of 15 over timescales of years. That is equivalent to a clock that loses or gains less than 1 second over the entire age of the universe. From the current period and the rate of period change, the characteristic age of a pulsar can be estimated. Young pulsars rotate fast and slow down quickly. Older pulsars rotate more slowly and have largely stable periods. Eventually, after tens to hundreds of millions of years, the rotation slows below the threshold needed to sustain beam emission and the pulsar goes dark, becoming one more silent neutron star drifting through the galaxy. Millisecond pulsars follow a different path entirely. These are neutron stars in binary systems that have been spun back up to extraordinary rotation rates by accreting mass from a companion star. As material falls onto the neutron star carrying angular momentum, the star spins faster, in some cases reaching rotation rates of hundreds of times per second. The fastest known millisecond pulsar, PSR J17482446 AD, located in a globular cluster called Terzan 5, rotates 716 times per second. Its surface at the equator moves at approximately 24% of the speed of light. Having been spun up and then left as the companion star exhausted itself, millisecond pulsars are in many cases billions of years old, yet still rotating at these extraordinary rates. Their periods are so stable that they are the most precise natural clocks known to exist anywhere in the universe, more accurate than any atomic clock humans have built. The same object that is the most precise natural clock is also, if you happen to be in the wrong place, one of the most lethal environments in the known universe. The beam of a millisecond pulsar spans the full electromagnetic spectrum from radio through optical, X-ray, and gamma-ray wavelengths, with the highest energy emission concentrated near the magnetic poles. The total power radiated in the beam can reach 10 to the power of 26 watts or more. Within the beam, particles are accelerated to Lorentz factors of millions, meaning they carry millions of times their rest mass energy. Model-dependent estimates suggest that at 10 light-years distance, a planet swept by the beam of a powerful millisecond pulsar would receive a radiation dose per sweep comparable to a significant fraction of the annual safe exposure limit for a human, delivered in milliseconds, hundreds of times per second. The figures depend strongly on beam geometry, spectrum, and the pulsar's specific properties, but the direction of the effect is not in doubt. Consider what that means for a planet in the beam's path. The pulsar rotates 716 times per second. Each rotation sweeps the beam across the sky. A planet lying along that beam receives a pulse of radiation 716 times every second, each pulse arriving in milliseconds, each carrying a dose of ionizing radiation that over the course of a day, a week, a year, would strip away any atmosphere, sterilize any surface, and leave no chemical process capable of sustaining life anywhere within reach of the beam. The first planets ever confirmed around any pulsar were discovered in 1992 by Alexander Wulshan and Dale Frail using the Arecibo Observatory. They orbit PSR B 1257 plus 12, a millisecond pulsar. Those planets were detected not by observing them directly, but by the tiny regular variations they induce in the pulse arrival times, as their gravitational influence shifts the pulsar's position relative to Earth. Whether any of them fall within the beam's sweeping path, and what that means for their surfaces, has not been directly determined. They are worlds orbiting one of the most precise clocks in the universe, and potentially one of the most lethal radiation sources within their neighborhood. The same timing precision that makes millisecond pulsars dangerous also makes them instruments. Pulsar timing arrays are networks of millisecond pulsars distributed across the sky, monitored over years for correlated deviations in their pulse arrival times. A gravitational wave passing through the galaxy stretches and compresses space-time, and that stretching shows up as a specific pattern of correlated timing shifts across all pulsars in the array simultaneously. In 2023, multiple independent collaborations reported evidence consistent with a gravitational wave background, a diffuse sea of low-frequency gravitational waves likely produced by merging supermassive black hole binaries throughout the universe, detected not by any purpose-built gravitational wave detector, but by the accumulated timing records of dead rotating stars. The most precise natural clocks known to science. A sterilizing beam sweeping through space hundreds of times per second. Both descriptions apply to the same object. The lighthouse and the weapon are the same structure, seen from different directions. On the 27th of December 2004, the instruments were not ready for what arrived. Gamma-ray detectors aboard multiple spacecraft saturated simultaneously. Instruments designed to measure the most energetic events in the universe went beyond their maximum readable range. The RESI spacecraft, the Ramati High Energy Solar Spectroscopic Imager, recorded a signal so intense it reflected detectably off the moon. Not off a mirror, not off a telescope, off the moon. The reflected signal was measurable. On Earth, the ionosphere, the electrically charged layer of the upper atmosphere that normally responds only to activity from the sun, showed a disturbance equivalent to a significant solar flare. The burst lasted approximately 0.2 seconds at its initial peak. A pulsating tail of emission continued for several minutes afterward. The source was located approximately 50,000 light-years from Earth, on the far side of the galaxy. In those 0.2 seconds, it released an estimated energy equivalent to what the Sun emits across all wavelengths in approximately 250,000 years. That energy had been traveling for 50,000 years before it reached us. It crossed half the diameter of the Milky Way, spreading outward through space, attenuating with every light year of distance, and when it finally arrived at Earth, it was still powerful enough to measurably alter the upper atmosphere of our planet. No other event of confirmed astrophysical origin has produced a comparable effect on Earth from that distance in the era of modern instrumentation. To understand what produced it, you need to understand what a magnetar is. Not just what it is made of, but what its magnetic field actually does to matter, to space, and to anything that comes near it. Begin with a number. Earth's surface magnetic field is roughly 0.5 Gauss. A refrigerator magnet produces a field of about 50 Gauss, 100 times stronger than Earth's. The strongest MRI machines used in hospitals operate at around 30,000 Gauss. The strongest sustained magnetic fields ever produced in any laboratory on Earth reach approximately 450,000 Gauss. An ordinary neutron star carries a surface field of around 10 to the power of 12 Gauss, 1 trillion Gauss, roughly 2 billion times stronger than the most powerful magnet humans have ever built. A magnetar's field is approximately 1,000 times stronger than that, 10 to the power of 15 Gauss. 1 quadrillion Gauss. At that field strength, the magnetic field energy density near the surface of the star exceeds the energy density of the matter itself. The field is not a property of the star in the way that a bar magnet has a field. The field dominates the star. It restructures the star's own crust. It does not sit inside the neutron star. In a very real physical sense, the neutron star sits inside the field. How magnetars form is not fully resolved. The leading framework attributes their extreme fields to a dynamo process operating in the first seconds after the neutron star's birth. If the newly formed neutron star is rotating very rapidly, convective motion within its still liquid interior can amplify a seed magnetic field through a self-reinforcing feedback process. The same basic mechanism that generates Earth's magnetic field, but operating at rotation rates and densities so far beyond anything in Earth's interior that the comparison barely holds. Simulations suggest that initial rotation periods shorter than a few milliseconds are necessary. Only a small fraction of collapsing stellar cores rotate fast enough to meet that condition. Of the roughly 1 billion neutron stars estimated to exist in the Milky Way, only about 30 magnetars have been identified. The others either never develop the right initial conditions or are currently in quiet phases that make them effectively invisible to our instruments. The magnetic field of a magnetar does not sit passively once formed. It exerts stress on the neutron star crust, the layer of nuclear pasta and neutron-rich nuclei described in the previous chapter, the strongest solid material in the universe. As the field evolves and shifts over time, the mechanical stress it imposes on that crust builds. Picture the strongest material that exists, matter 10 billion times stronger than steel, being slowly bent by the most powerful magnetic field that exists. The crust resists. The field pushes harder. The stress accumulates over months or years or decades until something gives. When the crust fractures, the event is called a starquake. The magnetic field snaps into a new configuration in a fraction of a second, releasing the stored energy impulsively. A fireball of gamma-ray and X-ray emitting plasma erupts from the surface. This is what happened to SGR 1806-20 on the 27th of December 2004. That magnetar had been known as a repeating source of gamma-ray bursts since the 1980s, producing smaller flares periodically as its crust adjusted to the stress of its evolving field. The December 2004 event was its largest recorded flare by an enormous margin. The initial spike lasted 0.2 seconds, during which the luminosity reached approximately 10 to the power of 47 watts, several orders of magnitude above the Eddington luminosity, the threshold at which radiation pressure overcomes gravity. The pulsating tail that followed was modulated at the star's rotation period of 7.56 seconds, meaning the fireball of plasma was anchored to the star's surface, rotating with it, sweeping its emission across space like a slower and incomparably more destructive version of a pulsar beam. The tail lasted roughly 380 seconds before fading below detection thresholds. The event was detected by an array of spacecraft that happened to be correctly oriented, including RESI, the Mars Odyssey Orbiter, the Rossi X-ray Timing Explorer, and Integral. The fact that instruments aboard a spacecraft orbiting Mars also registered the event gives some sense of its absolute intensity. By triangulating arrival times across spacecraft at different positions in the solar system, scientists confirmed the source location and reconstructed the event's light curve with high precision. The question of what this event would have meant at closer range is one that astrophysicists have calculated directly. At 50,000 light-years, the 2004 flare was detectable, briefly disruptive to our ionosphere, and otherwise harmless. At 10 light-years, the same event would deliver a gamma-ray dose to Earth's atmosphere sufficient to significantly deplete stratospheric ozone globally. The ozone layer would not recover for years. Surface life would be exposed to elevated ultraviolet radiation throughout that period, disrupting photosynthesis, damaging DNA in surface-dwelling organisms, and collapsing the food chains that depend on primary production. At 1 light-year, the effects would be substantially more severe. No known magnetar currently lies within 10 light-years of Earth. The nearest confirmed magnetar, SGR 1935 plus 2154, which in 2020 became the first magnetar associated with a fast radio burst, is located roughly 30,000 light-years away. We are safe from what these objects produce, not because of any shield or any defense, but purely because of the distance between us and them. The distances of space are the only protection that exists, and they are, for now, sufficient. A magnetic field strong enough to restructure the strongest solid material in the universe. A field that stores the energy equivalent of 250,000 years of solar output and releases it in 1/5 of a second. A field so intense that the neutron star matter surrounding it cannot hold it still. The danger a magnetar represents is not gravity, not temperature, not particle flux in any ordinary sense. It is the stored energy of a magnetic field that dwarfs every other magnetic field in the known universe, straining against the only material strong enough to contain it, and periodically winning. At 7:35 in the morning on the 23rd of February 1987, something passed through the Earth that almost nothing can pass through. Neutrinos are among the most ghostly particles in physics. They have almost no mass. They carry no electric charge. They interact with ordinary matter so rarely that a neutrino could travel through a wall of solid lead a light year thick and most likely not touch a single atom. Billions of them are passing through your body right now, produced in the sun's core, and you will never feel any of them. They are as close to nothing as a particle can be while still existing. At 7:35 that morning, a burst of them arrived at 3 separate detectors on Earth. The Kamiokande 2 detector in Japan recorded 12. The Irvine, Michigan Brookhaven detector in the United States recorded 8. The Baksan Neutrino Observatory in the Soviet Union recorded 5. 25 neutrinos in total, detected across 3 facilities on 2 continents within a window of 13 seconds. 25 detections of a particle that almost never interacts with anything. The only way to detect 25 of them in 13 seconds is if an almost incomprehensible number of them arrived at once. 3 hours later, the first optical brightening of what would become supernova 1987A was recorded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, approximately 168,000 light-years from Earth. Those 25 neutrinos were the first confirmed detection of astrophysical neutrinos from outside the solar system. They arrived before the light because neutrinos, interacting only through the weak nuclear force and gravity, passed directly through the collapsing star, while the optical shockwave took hours to reach the stellar surface and escape as visible light. The sequence confirmed, in direct observational terms, the theoretical picture of core collapse that had been developed over the preceding decades. The neutrinos came first. The light followed. The model was right. A core collapse supernova begins as described in the previous chapter on neutron stars. The iron core of a massive star collapses in under a second, forming a neutron star or, for the most massive progenitors, a black hole. The outer layers of the star, still falling inward when the core suddenly stiffens and rebounds, collide with the rebounding shockwave. The energy deposited by that collision, along with the immense neutrino flux streaming outward from the forming neutron star, drives the outer envelope of the star outward at velocities between 10 and 30,000 kilometers per second. The star's surface brightens from obscurity to a luminosity that can, for weeks, rival the entire output of its host galaxy. The total energy released is approximately 3 times 10 to the power of 46 joules in roughly 10 seconds. To put that figure alongside something encountered earlier in this documentary, it is comparable to the total energy the Sun will emit across its entire 10 billion year lifetime, released in the time it takes to make a cup of tea. 99% of that energy is carried not by light but by neutrinos, produced in their trillions during the neutronization of the collapsing core. The brilliant optical display, which at 168,000 light-years was bright enough to be seen with the naked eye from Earth for several months, represents only about 1% of the total energy output. It is the visible surface of an event whose true scale is almost entirely invisible to ordinary instruments. A second category of supernova operates through a completely different mechanism. Type Ia supernovae involve the thermonuclear destruction of a white dwarf, the dense remnant of a low to intermediate mass star, when accreted mass from a companion pushes it past the Chandrasekhar limit of 1.4 solar masses. This ignites runaway carbon fusion that destroys the star completely in under a second, releasing approximately 10 to the power of 44 joules and leaving no compact remnant behind. No neutron star, no black hole, no core. Just an expanding cloud of enriched debris, and the light from the explosion itself. The killing zone of a core collapse supernova extends far beyond what the optical display suggests. Within approximately 50 light-years, Some calculations suggest the neutrino flux reaches a density sufficient to deliver biologically significant ionizing doses to tissue. This seems impossible given everything said above about how rarely neutrinos interact with anything. But the sheer number produced in a core collapse, on the order of 10 to the power of 58, is large enough that even an almost impossibly small interaction probability produces real biological consequences at close range. This remains the more contested part of the killing zone model. The dominant hazard mechanisms at greater distances are generally considered to be atmospheric rather than neutrino-driven. Beyond 50 light-years, the sustained output of the supernova remnant takes over as the primary threat. As the shockwave expands outward through the years following the explosion, heating surrounding material, it produces a sustained output of X-ray and gamma-ray emission. Any planet within roughly 25 to 30 light-years would receive sufficient ionizing flux to destroy a significant fraction of stratospheric ozone, not in a single flash, over years. The ozone layer would be progressively depleted by high-energy radiation arriving continuously from the expanding remnant, and it would not recover quickly. Surface life would be exposed to elevated ultraviolet radiation from the planet's own star throughout the recovery period, which could span decades. Photosynthesis would be disrupted. DNA in surface-dwelling organisms would be damaged. The food chains, depending on primary production at the ocean surface, would collapse. The damage is slow, quiet, and sustained. It does not look like an explosion. It looks like a world gradually becoming less hospitable to the chemistry that supports life, over a timescale long enough that the cause and the effect might not be obviously connected in any geological record that survived it. Whether a nearby supernova has already done this to Earth is a question the geological and fossil record has been examined for, with results that are suggestive but not conclusive. The end Ordovician mass extinction, approximately 445 million years ago, eliminated an estimated 85% of marine species. It is the second largest extinction event in the fossil record. It has two distinct phases: an initial extinction pulse associated with glaciation and sea level fall, followed by a second pulse during the subsequent warming. The two-phase structure is unusual. One proposed explanation is that the first pulse was triggered or significantly worsened by ozone depletion from a nearby gamma-ray burst or supernova, with shallow water, high ultraviolet exposed marine communities showing disproportionate losses relative to deeper water fauna, exactly the pattern you would expect if elevated surface ultraviolet radiation were the kill mechanism. The hypothesis is contested. The glaciation signal in the geological record is robust and provides a sufficient explanation for much of the extinction pattern without invoking an astrophysical cause. No definitive physical signature of a nearby supernova from that period has been confirmed. Iron 60, the radioactive isotope produced in supernova nucleosynthesis and detectable in sedimentary deposits, would be the clearest evidence. Iron 60 anomalies have been detected in deep-sea crusts and lunar samples corresponding to periods around 2.2 million and 8 million years ago, suggesting supernova events within a few hundred light-years during those intervals, but none yet tied to the Ordovician boundary. The absence of a confirmed signal does not rule out the hypothesis. A signal from 445 million years ago has had 445 million years of geological processing to be diluted, altered, or erased. Whether it ever existed in a form current instruments could detect is not known. What the supernova record does establish clearly is that the Sun's position in the Milky Way is not fixed. The solar system orbits the galactic center with a period of roughly 225 million years, oscillating above and below the galactic plane as it goes, passing through regions of varying stellar density and star formation activity. The probability of a supernova within the lethal radius is not uniform over geological time. It varies with where in the galaxy the solar system happens to be. Current estimates place the expected rate of supernovae within 50 light-years at roughly one event per several hundred million years. The nearest star currently considered a credible supernova candidate is Betelgeuse, a red supergiant at approximately 700 light-years distance. When it eventually explodes, it will be visible in daylight from Earth, a new light in the sky outshining everything except the sun and moon. It will be one of the most spectacular astronomical events in recorded human history. At 700 light-years, it is well outside the lethal radius for ozone depletion and far outside the neutrino damage zone. It is close enough to be extraordinary to watch, not close enough to be dangerous. That is the supernova from a safe distance. The same event at 25 light-years would not be a spectacle. It would be the beginning of a slow, quiet degradation of the atmospheric chemistry that stands between surface life and the full intensity of the sun's ultraviolet output. The most energetic event in this documentary so far, releasing in 10 seconds the energy the sun will produce over its entire lifetime, would not kill through its initial flash. It would kill through what it did to the sky in the years afterward. The killing zone is large, the damage is slow, and the signature it leaves in the rock and fossil record is faint enough that whether it has already happened to Earth remains, 445 million years later, a matter of active investigation. Somewhere in the universe today, a star died in a way that released more energy in a few seconds than the sun will produce across its entire 10 billion year lifetime. The explosion sent two narrow beams of gamma radiation racing outward in opposite directions at the speed of light. One of those beams is pointed away from us. We will never know this event happened. The other beam is pointed toward us. In a few hours, or a few days, a detector in orbit around Earth will register a flash of high-energy radiation from a random point on the sky. It will last anywhere from a fraction of a second to several minutes. Then it will be gone. This happens roughly once per day. That is the observational signature of a gamma-ray burst, and the number sounds manageable until you understand what it actually means. One per day is not the true rate at which gamma-ray bursts occur in the universe. It is the rate at which bursts happen to be pointed at Earth. The mechanism that produces a gamma-ray burst does not distribute its energy in all directions. It concentrates that energy into two narrow jets, launched in opposite directions along the rotational axis of the central engine. Each jet spans roughly 1 to 10 degrees of arc, a small fraction of the full sphere of directions. For a burst to reach our detectors, one of its jets must be aimed within that narrow angle directly toward Earth. The overwhelming majority of gamma-ray bursts in the universe occur with their jets pointed elsewhere. Those events go entirely undetected. They happen, they release their energy, and we see nothing. Correcting for this beaming geometry, the true rate of gamma-ray bursts occurring throughout the observable universe is estimated to be several hundred to perhaps 1,000 times higher than the detected rate. The universe's most energetic explosions are largely invisible, not because they are rare, but because they are narrow. Gamma-ray bursts divide into two distinct classes, each produced by a different catastrophic event. Short gamma-ray bursts last less than 2 seconds. They are produced by the merger of two compact objects, either two neutron stars or a neutron star and a black hole. These are objects that have been spiraling toward each other for millions or hundreds of millions of years, losing energy to gravitational wave emission with each orbit, their separation shrinking imperceptibly slowly over geological time until the final inspiral. In the last seconds before collision, they are moving at a significant fraction of the speed of light. The merger produces a rapidly rotating remnant surrounded by an accretion disk of hot dense material. That disk accretes over fractions of a second, and the resulting energy output launches twin relativistic jets. On the 17th of August 2017, two neutron stars that had been spiraling toward each other for an estimated billion years finally merged. The gravitational waves from that merger were detected simultaneously by the LIGO and Virgo observatories. Exactly 1.7 seconds later, a short gamma-ray burst was detected by the Fermi Gamma-Ray Space Telescope. For the first time, a gamma-ray burst had been directly connected to its source. The optical counterpart that followed, a kilonova, revealed spectroscopic signatures of heavy elements, including strontium and gold. Neutron star mergers are where the gold in your jewelry came from. The gamma-ray burst was a byproduct of the event that forged it. Long gamma-ray bursts last more than 2 seconds and typically extend to tens or hundreds of seconds in duration. Their origin is a core collapse event more extreme than an ordinary supernova. In a standard core collapse supernova, the infalling outer layers of the star are expelled by the neutrino-driven shockwave. In the event that produces a long gamma-ray burst, called a collapsar, the stellar core is massive enough and rotating fast enough that the collapsing material forms a thick accretion disk around the newly formed black hole rather than being expelled. That disk accretes rapidly. The energy output drives relativistic jets that punch through the still collapsing outer layers of the star and emerge from the stellar surface. The precise emission mechanism, whether internal shocks, magnetic reconnection, or a combination of both, remains debated. What is not debated is the scale. Material within the jet moves at Lorentz factors of typically 100 to 1000, meaning it carries 100 to 1000 times its rest mass energy as kinetic energy. The total isotropic equivalent energy of a long gamma-ray burst reaches between 10 to the power of 44 and 10 to the power of 47 joules. To give that number a reference point, the higher end of that range is comparable to or exceeds the total energy output of a core collapse supernova, itself the most energetic event examined in the previous chapter, including the neutrinos that carry most of the energy. Gamma-ray bursts concentrate that energy not as invisible particles, but as electromagnetic radiation, making them the most energetic electromagnetic events known to occur in the universe. The challenge of studying them is their brevity. A burst that lasts seconds produces an afterglow that fades over days. To study that afterglow, you need to point a telescope at the right location within minutes of the detection. The SWIFT satellite, launched by NASA in November 2004, was built to do exactly this. Its Burst Alert telescope detects and localizes a burst within seconds, and the spacecraft autonomously rotates to point its narrow-field instruments at the location within roughly 90 seconds. That rapid response has enabled measurements of burst afterglows at distances exceeding 6 billion light-years. The most distant confirmed gamma-ray burst, GRB 090423, occurred at a redshift of 8.2, when the universe was less than 630 million years old. We are observing explosions from a time before our solar system existed. At those cosmological distances, gamma-ray bursts are scientifically extraordinary, but not directly threatening to Earth. The danger becomes local when the geometry changes. Within a few thousand light-years, a burst with its jet directed at Earth would deliver a gamma-ray fluence sufficient to trigger global ozone depletion on a scale far exceeding anything a nearby supernova could produce. The irradiation itself would be brief, lasting seconds to minutes, but the ozone destruction it caused would persist for years, and the consequences for surface life would be the same slow, quiet environmental degradation described in the previous chapter. Elevated ultraviolet radiation, disrupted photosynthesis, collapsed food chains, a world that becomes gradually less habitable in the years following an event that itself lasted less than a minute. There is a critical difference between a gamma-ray burst and a supernova as a geological threat. A supernova leaves radioactive isotopes, particularly iron, 60, in the sedimentary record. That is how we know supernova events occurred near Earth roughly 2.2 million and 8 million years ago. A gamma-ray burst leaves no such trace. It produces no significant flux of radioactive isotopes at the target. The gamma radiation arrives, strips the ozone, and leaves. No chemical signature, no isotopic anomaly, no record in the rock. This returns to the end-Ordovician extinction discussed in the previous chapter. The absence of a confirmed iron 60 signal at the Ordovician boundary does not rule out an astrophysical cause. If the trigger was a gamma-ray burst, rather than a supernova, the absence of isotopic evidence is exactly what you would expect. The hypothesis cannot be confirmed by the geological record, but it also cannot be ruled out by it. That is simply the nature of the mechanism. The true rate of gamma-ray bursts occurring within lethal range of Earth over geological time is uncertain but not negligible. The burst rate in the Milky Way is estimated at perhaps 1 to a few events per million years. The fraction of those directed toward the solar system is small, constrained by the beaming geometry, but over hundreds of millions of years, the probability of a nearby directed burst becomes statistically meaningful. Whether one has already occurred and left no trace in the geological record is a question that may never be answered. One per day, detected. Many hundreds per day, occurring. The most energetic explosions in the universe are largely invisible, not because they are rare, but because the beams that carry their energy are narrow enough that most of them sweep through space without touching anything we will ever be able to see. The universe produces these events continuously. Most of them miss everything. Start as far out as possible, hundreds of thousands of light years from the center, where two narrow columns of plasma stretch outward from a single point, one above and one below, traveling at 99% of the speed of light. They extend for distances greater than 1 million light years in some cases, longer than the diameter of the Milky Way, carrying enough energy in their continuous outflow to heat the gas between entire galaxy clusters and suppress the formation of new stars across volumes of space larger than anything encountered so far in this documentary. These are relativistic jets. They are the first visible sign of what lies at their origin, and they are not rare. Structures like this have been observed extending from hundreds of active galaxies, each one marking a location where something is converting matter into energy with an efficiency that makes nuclear fusion look modest. Work inward along the jet toward its source. The object at the center is a black hole, not a dense star, not an extremely massive planet, a region of space-time from which the escape velocity exceeds the speed of light. Beyond a boundary called the event horizon, nothing, no matter, no radiation, no signal of any kind, can return to the universe outside. The event horizon is not a wall. It is not a surface you could touch or feel. It has no material substance. It is a geometric boundary, a threshold defined purely by the curvature of space-time, below which escape becomes not difficult but geometrically impossible. The universe on the other side of an event horizon is, in a precise mathematical sense, a different place from the universe on this side. Stellar mass black holes, with masses between roughly 5 and 100 times the mass of the Sun, form when the most massive stars exhaust their nuclear fuel and the core collapses past the point where even neutron degeneracy pressure can resist. Rather than forming a stable neutron star, the collapse continues. The outer layers may be expelled in a supernova, or in some cases may fall inward silently in what is sometimes called a failed supernova. A star that was shining brightly simply stops, and a black hole exists where it did not before. Black holes have been confirmed observationally through their gravitational effects on companion stars, through gravitational wave detections of merging black holes by LIGO beginning in 2015, and through direct imaging of the shadow cast by the supermassive black holes M87 times and Sagittarius A times by the Event Horizon Telescope in 2019 and 2022. Moving inward from the jet toward the black hole itself, the next zone is the accretion disk. Matter falling toward a black hole carries angular momentum and cannot fall straight in. It accumulates into a flattened rotating disk, like water circling a drain, but spanning distances of millions of kilometers. Within the disk, friction and magnetic turbulence transfer angular momentum outward, allowing material to spiral gradually inward. The gravitational energy released in this process heats the inner disk to tens of millions of Kelvin, producing intense X-ray emission detectable across billions of light years. The spectrum and variability of that emission carry information about the mass, spin, and geometry of the black hole, readable by instruments that will never come anywhere near the object they are measuring. Closer still is a region with no analog anywhere else examined in this documentary. Around a rotating black hole, space-time itself is dragged into rotation by the spin of the central mass. This is not a metaphor. The fabric of space-time, the medium through which light travels, and in which all physical events occur, rotates. The effect is called frame dragging, and it exists around any rotating mass, including Earth, where it is measurable but tiny. Near a rapidly spinning black hole, it becomes extreme. The ergosphere is the region outside the event horizon, where frame dragging is so strong that nothing, regardless of how much thrust it applies, can remain stationary relative to distant observers. Everything within the ergosphere is forced to rotate in the same direction as the black hole. Space itself moves, and nothing can resist it. Between the ergosphere's outer boundary and the event horizon, it is in principle possible to extract energy from the black hole's rotation. A process proposed by Roger Penrose in 1969 described how an object entering the ergosphere and splitting into two pieces, with one piece falling into the black hole on a specific trajectory, could result in the escaping piece carrying away more energy than the original object brought in. The deficit comes from the black hole's rotational energy. The black hole slows slightly. Energy is extracted from the geometry of space-time itself. The related Blandford-Znaic mechanism, in which magnetic fields threading the ergosphere extract rotational energy electromagnetically, is the leading explanation for how the relativistic jets observed at the very start of this chapter are actually launched. The jets that stretch for 1 million light-years begin here, in the dragged space-time just outside the event horizon. Now comes the question of what happens to anything that crosses the horizon. For a stellar mass black hole of 10 solar masses, the event horizon lies approximately 30 kilometers from the center. A falling observer would encounter danger long before reaching it. The tidal force across the diameter of a human body at 3,000 kilometers from a 1-0 solar mass black hole exceeds the tensile strength of biological tissue. The body would be stretched along the direction of fall and compressed perpendicular to it, drawn out into a lengthening thread of matter by the differential gravitational pull between its near side and its far side. Spaghettification, the stretching and eventual fragmentation of an infalling object by differential gravitational acceleration, would occur thousands of kilometers above the horizon. The event horizon itself would never be reached in any recognizable form. At supermassive scales, this relationship inverts completely. Ton 618, a quasar approximately 10.4 billion light-years distant, hosts a black hole with a mass of approximately 66 billion solar masses. Its Schwarzschild radius is roughly 1,300 astronomical units, larger than the entire solar system out to well beyond the Kuiper belt. At that scale, the tidal force across a human body at the event horizon is negligible. The curvature of space-time at the horizon of TON 618 is so gradual, spread across such an enormous volume, that a falling observer would cross the threshold without any local physical sensation that anything had changed. No stretching, no compression, no visible boundary. Just the ordinary appearance of space in all directions, and the quiet, permanent fact that the universe outside is now unreachable. That is what the event horizon actually is at supermassive scales. Not a dramatic crossing, a silent one. Beyond the event horizon, general relativity predicts a singularity, a point where density becomes infinite and the curvature of space-time becomes infinite, and the equations of general relativity break down entirely. Whether this represents a physical reality or a sign that general relativity is simply incomplete at extreme densities is unresolved. No observation from outside a black hole has ever penetrated the horizon. No theory has yet fully described what exists within. The information paradox sits at this boundary. General relativity predicts that anything falling into a black hole is lost to the exterior universe. Quantum mechanics requires that information cannot be permanently destroyed. Stephen Hawking's 1947 demonstration that black holes radiate thermally through quantum effects near the horizon appeared to worsen the problem rather than resolve it. The radiation carries no information about what fell in, implying that when the black hole eventually evaporates, the information about everything that ever crossed the horizon is simply gone. Whether information is genuinely destroyed, preserved in the Hawking radiation in some subtle form that has not yet been decoded, or encoded on the horizon itself through a mechanism not yet understood, is among the most actively debated problems in theoretical physics. There is no settled answer. There may not be one within the reach of any physics currently available. The black hole is not a single danger. It is a nested sequence of environments, each requiring different physics to describe, each more extreme than the last, arranged around a boundary that nothing has ever crossed and returned from. The jets that mark its location from a million light-years away are produced by the dragged space-time just outside it. The accretion disk that feeds it glows hotter than the surface of most stars. The ergosphere extracts energy from the rotation of space-time itself. The tidal forces outside the horizon of a small black hole would dismantle matter before it arrived. The horizon of a large one would be crossed in silence. And beyond it, at a point where the equations stop working and the questions stop having answers, something exists that no instrument will ever reach and no theory has yet described. That is where this chapter ends, not at a conclusion, but at a boundary. At the center of the Milky Way, 26,000 light-years from Earth, something sits in the dark that weighs 4 million times as much as the Sun. You cannot see it in visible light. The intervening space between Earth and the galactic center contains enough dust to reduce the optical light from that direction by a factor of roughly 10 trillion. 10 trillion times dimmer than it would otherwise appear. If you pointed the most powerful optical telescope ever built at the galactic center and stared for as long as you liked, you would see almost nothing. The center of our own galaxy is effectively invisible to human eyes, and to any instrument that operates in the wavelengths human eyes were built to detect. What we know about it came from infrared light, from radio waves, from X-rays and gamma rays that penetrate the dust with varying degrees of success. And what those wavelengths revealed, over decades of patient observation, was a neighborhood so extreme that the black hole at its center is almost not the most dangerous thing about it. Begin with the black hole itself. Sagittarius A is, by the standards of supermassive black holes, restrained. It accretes at a rate far below its Eddington luminosity, emitting at roughly 10 to the power of 33 watts in X-rays during its normal state. occasionally flaring to a few hundred times that level over periods of hours before subsiding. It produces no persistent relativistic jet. It does not outshine its host galaxy. Observed in isolation, without the context of where it sits and what surrounds it, Sagittarius A would not register as especially threatening. The context is everything. In the 1990s, two independent teams began a project that would take decades to complete. One was led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics. The other was led by Andrea Ghez at UCLA. Both teams were doing the same thing, tracking individual stars near the galactic center using infrared adaptive optics imaging, watching them move year by year, orbit by orbit, building up a picture of what was pulling them. What they found was this: a cluster of stars, now called the S-star cluster, moving at velocities of thousands of kilometers per second in tight ellipses around a dark central mass. The star designated S2 completes one full orbit every 16 years. At its closest approach, it moves at nearly 3% of the speed of light. The orbital mechanics of these stars required the central mass to be approximately 4 million solar masses confined within a volume smaller than our solar system. No known configuration of normal matter, no cluster of dim stars, no concentration of gas, no exotic but non-singular object could produce that mass in that volume. The object at the center was a supermassive black hole. Genzel and Ghez shared the 2020 Nobel Prize in Physics for this work, but the S-star observations gave more than a confirmation of the black hole's existence. As S2 passed through its closest approach in 2018, the gravity collaboration measured both the gravitational redshift of its light and a relativistic Doppler shift consistent with the predictions of general relativity. In 2020, they confirmed the Schwarzschild precession of S2's orbit, the slow rotation of the orbital ellipse around the central mass, directly analogous to the precession of Mercury's orbit that provided one of the first confirmations of Einstein's theory a century earlier. The galactic center, hidden behind dust and unreachable by any physical probe, is being used as a laboratory for the strongest gravitational field accessible to direct stellar observation anywhere in the universe. Now move outward from the black hole and consider what surrounds it. Within the central parsec, a sphere roughly 3.26 light-years in radius around Sagittarius A, the stellar density reaches approximately 10 million times the density of the solar neighborhood. The stars in our part of the galaxy are separated by distances measured in light-years. In the central parsec, they are separated by distances measured in light-weeks. This is not a region where stars drift quietly through space. It is a region where close encounters between stars happen on timescales that would be extraordinary anywhere else in the galaxy, but are routine here. Among those stars are massive young ones, tens of times the mass of the Sun, existing in configurations that standard star formation theory cannot explain. The tidal forces near Sagittarius A should prevent any gas cloud from collapsing into stars at these distances. The stars should not be there. They are there. How they formed remains an open question in galactic center astrophysics. Massive stars live fast and die in supernovae. A region this dense with massive stars has a supernova rate substantially exceeding that of comparable volumes in the galactic disk. Each supernova injects energy into an already dense and turbulent interstellar medium and accelerates cosmic rays to high energies. The cumulative effect across the central 100 light-years is an environment hostile to planetary atmospheres and biospheres through multiple overlapping mechanisms simultaneously. Elevated cosmic ray flux, frequent nearby supernovae, intense X-ray and ultraviolet irradiation from the dense population of massive stars, and periodic energetic outbursts from Sagittarius A, whose current quietness is, as the evidence makes clear, not its permanent condition. Those outbursts are written into the structure of the galaxy itself in a feature discovered in 2010 using the Fermi Gamma Ray Space Telescope. Extending 25,000 light-years above the galactic plane and 25,000 light-years below it, two enormous lobes of gamma-ray emission, now called the Fermi bubbles, encompass a volume larger than the visible disk of the Milky Way. They are larger than the galaxy they extend from. The energy required to inflate them is estimated at roughly 10 to the power of 55 joules. To give that number a reference, the total energy released by a core collapse supernova is approximately 10 to the power of 46 joules. The Fermi bubbles required roughly 1 billion times more energy than a supernova to produce. That energy came from somewhere within the last few million years, recent enough in geological terms that early members of the genus Homo were already present on Earth when whatever produced the bubbles was at its peak. Two explanations have been proposed, and neither has been definitively confirmed. The first attributes the bubbles to a period of significantly elevated accretion onto Sagittarius A, during which the black hole was active at a level comparable to a low-luminosity active galactic nucleus, driving outflows that inflated the bubbles over 1 to 3 million years. The second attributes them to an intense burst of star formation in the central region, with the combined winds and supernovae of a large population of massive stars driving the outflow rather than the black hole itself. Both are physically plausible. The data collected so far has not been sufficient to distinguish between them. Work continues using Fermi data and observations from eROSITA, which mapped the bubbles in X-ray wavelengths in 2020 and found them to be even larger in that energy band than the gamma-ray observations had indicated. What the Fermi bubbles establish, regardless of which mechanism produced them, is something important about how to evaluate Sagittarius A. The current quietness of the black hole is a snapshot. It is not a permanent condition. Within the last few million years, the galactic center was releasing energy at a rate sufficient to drive a structure 1 billion times more energetic than a supernova outward through the galaxy's halo. The transition from that active state to the current one required no external event. It was simply a change in the supply of gas reaching the central accretion zone. It could change again. The galactic center is dangerous in a way that differs from every previous subject in this documentary. Every previous chapter described a single object with a defined mechanism and a calculable lethal radius. The galactic center is not a single object. It is a volume of space in which the density of extreme things, massive young stars dying in supernovae, a supermassive black hole with a documented history of violent outbursts, and the radiation environment sustained by all of them operating simultaneously, produces conditions hostile to the long-term stability of any planetary system within a region, hundreds of light-years in extent. No single mechanism dominates. The cumulative environment is the hazard. It is not a point source. It is a neighborhood. From 26,000 light-years away, the solar system sits comfortably outside it. The galactic center is observable from this distance, measurable, and scientifically productive precisely because we are not inside it. The stellar orbits that confirm general relativity, the bubbles that revealed a billion supernova-scale event in our galaxy's recent past, the evidence for a supermassive black hole at the heart of the Milky Way, all of it has been learned from a safe, observational distance. What the S-star cluster orbits and the Fermi bubbles together reveal is a place that has produced some of the most important scientific confirmations of the last century. It has also produced conditions under which nothing with an atmosphere and a surface could persist for long. Both things are true of the same location, and both are worth holding in mind. Every subject examined in this documentary so far has had a boundary. A neutron star has a surface, a magnetar has a magnetosphere with a calculable edge, A black hole has an event horizon. Even the galactic center, the most spatially diffuse danger examined in the previous chapter, could be described as a region hundreds of light years across with conditions that, outside its boundary, no longer apply. What comes next has no such boundary. The danger is not located at a point or confined to a region. It fills a galaxy. In 1966, Hulton Arp published an atlas of peculiar galaxies, a catalogue of objects that did not fit neatly into the standard classifications of galactic morphology. Object number 220 in that catalogue was noted for its unusual shape and passed over without further comment. It was one entry among hundreds of odd-looking galaxies, unremarkable in its oddness, catalogued and filed. Subsequent observation has been less restrained in its assessment. ARP 220 is located approximately 250 million light-years from Earth in the constellation Serpens. It is the product of a collision between two spiral galaxies that began roughly 700 million years ago. As the two galaxies merged, their gas was compressed and funneled into the central region of the combined system. That central region, roughly 5,000 light-years across, now contains one of the most extreme star-forming environments known to exist anywhere in the observable universe. Within that region, stars are forming at a rate of approximately 200 solar masses per year. The Milky Way forms stars at a rate of roughly 1 to 2 solar masses per year across its entire disk. ARP 220 produces the equivalent of 100 Milky Ways worth of new stars every year, concentrated into a volume representing a small fraction of a normal galaxy's size. Massive stars live fast. A star of 25 solar masses exhausts its nuclear fuel and explodes as a supernova in roughly 7 million years. When star formation proceeds at 200 solar masses per year, the pipeline of massive stars moving toward their deaths runs continuously. The death rate keeps pace with the birth rate. The consequence is a supernova rate of approximately 1 event per year within the central starburst region. 1 supernova per year in a volume 5,000 light-years across. In Chapter 9, a supernova within 25 to 30 light-years was described as sufficient to destroy a significant fraction of Earth's ozone layer and expose surface life to years of elevated ultraviolet radiation. Inside ARP 220, that scale of event occurs roughly once every 12 months, and the previous supernova remnant has not yet finished expanding before the next one begins. The interstellar medium within ARP 220 is perpetually churned by overlapping shockwaves, continuously flooded with cosmic rays, and permanently irradiated by the X-ray and gamma-ray emission of supernova remnants in every stage of evolution simultaneously. No stable planetary atmosphere could be maintained within that environment. The concept of a biosphere anywhere inside ARP 220 is not merely improbable. It is physically precluded by the sustained energy input from stellar death alone, before the central black hole is even considered. This is danger operating at galactic scale, produced not by any single extreme object, but by the cumulative output of an entire population of stars dying in concentrated rapid succession. But star formation is only one of the two engines driving ARP 220. A galaxy is not simply a collection of stars. At its center sits a supermassive black hole. In a quiescent galaxy like the current Milky Way, that black hole accretes slowly and contributes little to the galaxy's overall energy output. When gas is driven into the central regions in large quantities, as happens when two galaxies collide and their gas is compressed inward, the situation changes. The accretion rate increases. The inner accretion disk heats to tens of millions of Kelvin. The luminosity of the central region can rise until it exceeds the combined output of every star in the galaxy. The galaxy's center becomes an active galactic nucleus. The most luminous class of active galactic nucleus is a quasar. When Martin Schmidt identified the redshift of the object designated 3C273 in 1963, placing it at a distance of approximately 2.4 billion light-years, the implication was immediately unsettling. Something that appeared as a faint point of light in optical images was producing a luminosity approximately 100 trillion times that of the Sun. The most energetic quasars produce luminosities up to 10,000 times the total output of the Milky Way, sustained continuously by accretion onto black holes of billions of solar masses. A single compact region at the center of a galaxy, outshining everything else in that galaxy combined by a factor of 10,000. The reach of a luminous quasar extends far beyond its host galaxy. Quasar winds, driven by radiation pressure on surrounding gas, can expel material from the host galaxy at velocities of thousands of kilometers per second, stripping the gas supply needed for future star formation and effectively shutting down the galaxy's ability to make new stars over timescales of hundreds of millions of years. This process, called quasar feedback, is thought to be one of the primary mechanisms linking the growth of supermassive black holes to the large-scale properties of the galaxies they inhabit. The black hole at the center of a galaxy does not merely respond to its environment. At sufficient accretion rates, it determines it. In galaxy clusters, jets from an active central black hole propagate outward into the surrounding intergalactic gas. Inflating lobes of radio-emitting plasma extending hundreds of kiloparsecs beyond the visible edge of the host galaxy. The mechanical energy deposited heats the intergalactic medium across volumes measured in millions of light-years, suppressing the cooling flows that would otherwise funnel fresh gas back into the galaxy and fuel new generations of star formation. A single active galactic nucleus can regulate the thermal state of gas across a volume larger than most galaxy clusters. The influence extends beyond the galaxy's neighborhood. Across the cluster itself, galaxy collisions drive both processes simultaneously. When two galaxies interact gravitationally, the tidal forces disrupt the ordered rotation of their gas disks, driving gas inward. That inflow feeds star formation in the central regions and simultaneously supplies the central black hole. The antennae galaxies, a pair of colliding spirals approximately 22 million light-years from Earth, are currently in an intermediate stage of merger, their star formation rates already elevated roughly tenfold above their pre-merger state. They represent what ARP-220 looked like hundreds of millions of years ago, the starburst and AGN activity just beginning. The Milky Way and Andromeda will reach this same stage in approximately 4.5 billion years when their own collision begins. At the extreme end of the merger sequence, the result is ARP-220, a single disturbed remnant with its central gas compressed, its star formation rate at hundreds of solar masses per year, its central black hole freshly supplied with fuel. The starburst and the active nucleus are not separate consequences of the collision. They are concurrent responses to the same inflow of gas, each reinforcing the other's environmental impact, each making the other's effects more difficult for anything within the system to survive. A planet located anywhere within a starburst galaxy like ARP-220 would face not one overwhelming threat, but an accumulation of overlapping ones. Cosmic ray bombardment from hundreds of recent supernova remnants, X-ray irradiation from the active nucleus, ultraviolet flooding from thousands of newly formed massive stars, periodic disruption from supernova shockwaves propagating through the interstellar medium. There is no refuge within the system. Every previous subject in this documentary, however extreme, operated within a bounded region. A neutron star's danger extended thousands of kilometers. A magnetar's reached light-years. The galactic centers covered hundreds of light-years. ARP-220's danger fills the entire galaxy. There is nowhere within it that is outside the environment. The environment is the galaxy. What makes this more than a description of a distant, extreme object is a fact that bears stating directly. The Milky Way's current quiescence is not a permanent condition. It is a phase. Galaxy interactions, starburst episodes, and active galactic nucleus activity are recurring features of galactic evolution, driven by the continuing large-scale structure of the universe as gravity draws galaxies together over cosmic time. The Milky Way has been through periods of elevated star formation and black hole activity before. It will go through them again. Andromeda is already approaching. The collision is approximately 4.5 billion years away. That is a long time by any human measure. It is not a long time by the measure of what this documentary has been describing.